Hi, everyone. My name is Joe Rozek. I'm a developer relations engineer at ARM. Quick little bit about me. I've been a developer for about 8 years. I started out as an environment artist, moved to being a technical artist, and then into engineering. So I've had a lot of experience working in all the different ways you have to optimize an application or an app. One thing I do like to ask is if you have any additional questions, please feel free to hit me up on Twitter. It's a really great way for us to have a conversation on optimization, get engaged with the rest of the ecosystem, and share any sorts of documentation. So that way, anyone who has similar questions can get their answers too. But we have a lot to get covered, so let's go ahead and kind of jump into it. So today we will be talking about mobile systems, textures, geometry, shaders, frame rendering, and then a few VR graphics tips at the end. So let's go ahead and jump in. So to kind of understand why you need to make the choices you do when optimizing for a mobile set of hardware is it's kind of good to understand what's going on in a desktop system. So typically, this is your typical gaming desktop. It has a discrete CPU, GPU, and DRAM. The typical power budget is going to be anywhere from between 225 and 370 watts for a mid-end machine. All this power is going to eventually come out of the system in some form of heat. Drawing this much power, the system is going to need a significant amount of cooling. So you're going to have multiple fans blowing 100 cubic feet per minute of air over some very large heat sinks, allowing it to dissipate the generated thermal waste. And when you go ahead and take a look at a mobile system, here we'll be kind of looking at a phone. It uses a system on chip with the CPU and the GPU and their supporting components in a single silicon die. The DRAM is a separate piece of silicon as it uses a different manufacturing process, but it is typically stacked on top of the main logic die in an arrangement called package on package. For a smartphone, the total sustainable power budget for the main SoC and DRAM is somewhere between 2 and 3 watts. This is depending on the device and certain environmental factors. This is so small because the system relies exclusively on passive cooling. There are no fans, no high area heat sinks, and an efficient way to pull heat away from the device. So making gaming content use the system as efficiently as possible is critical for being able to achieve sustainable and high-end mobile graphics. This is also the same with the Quest. It's essentially just a mobile system put on someone's face. So it's going to be even more important because this is going to be right up against right up on someone's face, and the noticeable heat and the performance issues are going to be just that much easier to notice. So at the end of the day, everything we're doing is about bandwidth because bandwidth is power and heat. So we need to do everything possible to reduce that. So let's go ahead and take a look at textures. This one is pretty straightforward and very common across the industry, and that is please use texture atlases. Texture atlases are a really great way to save draw calls, to reduce the amount of times you're having to call the textures on the GPU. This can reduce bandwidth significantly. The scene you kind of see here is almost everything that's highlighted is using this one texture. So that way we don't have to call 4 different textures. It can all be set up on one material based on how you kind of have the UV setup. It's really, really efficient. The next really good way to save some bandwidth is by using mip mapping. For everyone who knows mip maps, one thing I have to kind of personally admit is it took me a little while to warm up to using them, since back in mobile, memory was king and it could cause crashes very easily if you went over in memory because it was very limited. So, but the way mip maps work is the further the area you're rendering is away from the player, it is going to use a down-resed copy of the texture. This is going to allow the GPU not to have to render a 1024 all the way super far away from the user. Instead, it can use a 512 or even a 256. This is going to save a ton of bandwidth, and it's also going to make the texture look a lot better. You're going to avoid what's called the texture aliasing effect. And this is where the image can kind of look a little bit crunchy when it's further away. This is because the GPU and the screen are trying to figure out how to put a 1024 texture only across just, let's say, 20 pixels. It's going to have to squish it down. It's going to have to make it look really crunchy and bad. So this is a really good way to also improve the texture quality of your app. Another thing to go ahead to look at is texture filtering. Generally, I suggest looking at two different options, bilinear and trilinear. Trilinear is going to be significantly more expensive than bilinear, and it's just going to kind of depend on how important the object is to you. My general suggestion is to be using bilinear with 2x anisotropic. This is going to give you a very good look, and it's going to perform better than trilinear with one anisotropic, and either look just as good, if not better, at the end. I'll also suggest you try to keep your anisotropic level low. Using anything higher than 2 is just going to cause additional bandwidth. It's going to reduce your battery. It's going to be expensive. So go ahead and try to avoid that anywhere you can. Next, let's go ahead and talk about texture compression. This is something that's very, very common nowadays. Generally, it's taken care of for you within your engine, or your engineers have it set up for you. But what texture compression is, it's taking an image like we have one here, and then going to be able to reduce it and make it easier for the GPU to call upon it. Here, I will always suggest you use ASTC. ASTC was developed by us here at ARM with conjunction of AMD. This was really helpful because it's going to give you a whole bunch of options of block sizes, so you can reduce or increase the amount of compression needed depending on the object. I suggest ASTC over ESTC, even just from a point of being a developer of, if you look at the image we have showing here, the differences in the compression is significant. ASTC looks a lot better, and it's even lower memory. So go ahead and start using that where you can. ASTC can feel a little bit intimidating at first because there's all these block sizes. You don't really know which one you need to use. What I'll suggest is go ahead and start with 5x5 or 6x6 blocks. This is a very good set of compression that's going to kind of get you where you want. If you find objects in Atlas or texture are very small on screen, you don't need to use them very much, they're very far in the distance, go ahead and try raising that up a little bit. If you find the user's getting very close to some content, it still looks a little crunchy and you think you can get away with it, go ahead and lower it a little bit and start playing with it from there. Next little bit will be to use Power of 2 with all your textures. This is, again, pretty straightforward. There's lots of tools or Photoshop or anything just to add a little bit of padding to be there. But if your textures aren't a Power of 2, you're not going to be able to generate bitmaps. A lot of engines won't allow you to do the texture compression. And this is going to be significant bandwidth hits to your project. And that's going to cause inefficiency. It's going to generate more heat, and it's just going to be bad for everyone involved. So the textures don't have to be square. If the height or the width are just a Power of 2, it's going to be fine. Such as if your image is 512 by 1024, it will be fine and be perfectly compressed. Next, consider doing some texture channel packing. Generally, you see this with any sort of map that's going to be single channel. Roughness, smoothness, or metallic is really good options. It can be applied to really any texture map, though. One really common use we're seeing it with the hand-painted styles is using the alpha channel to include some specularity to just kind of add that little bit of extra to the project. So let's go ahead and talk about some geometry. Geometry is a wonderful way to reduce bandwidth as well, because everything you're putting on the screen needs to be processed. So one of the biggest ways I found to help reduce geometry is with normal maps. Normal maps are fantastic. If a piece of your app or a piece of your geometry isn't being rendered to this or isn't a part of the image's silhouette, you can generally bake that out into a normal map, depending if this fits your art style or not. Normal maps are really cheap compared to the vertices you're going to have to be rendering. It's just one extra texture. It's going to be a few more texture fetches, but it's going to be really performant versus your other options. Another suggestion would be to avoid small triangles. Small triangles are a problem because if you kind of look at this model up here, it looks great close up, get a lot of detail, but when that gets further away, a lot of these triangles are kind of wasted. If a triangle, if you can't really notice a triangle within the space of 1 to 10 pixels, that's generally kind of a wasted triangle. But the GPU still has to process all of these, and it can increase the cost quite a bit. with that model so far away, we're having to render a ton of geometry that isn't really adding anything to the frame. So try to make sure each model will create at least 10 to 20 propagnants per primitive. So kind of in the same vein, but a little bit different would be to avoid long, thin triangles. You generally see this on some beveled edges and the such, but these are bad for the similar reasons as the small triangles, but they're also considerably worse because they go across multiple tiles. So with a mobile GPU, you're going to be rendering things in these little chunks on your screen. And when a really long and thin triangle goes across multiple levels, it's going to cause the GPU extra work to render out that tile across multiples of those. So go ahead and avoid these wherever you can. It's really important and can save you quite a bit of rendering power in the end. So a really good way to avoid using long thin triangles and micro triangles, but also keeping a really high visual look, is the use of LODs. Like mipmaps, these were something I really kind of struggled with early in my career to kind of adapt to, but once you start using them and see the benefits of them, they're wonderful. So they function just like mipmaps do, but for meshes. The further away it is, it uses a lower resolution one. The closer it is, it uses a higher resolution one. These are generally made by artists, or there's a lot of tools out there nowadays that can kind of help you. As long as your image is kind of keeping the same general silhouette, it works great. I suggest each step, kind of go down, try to have the geometry as you go. And this is going to save you a ton, especially if things are moving back and forth in your scene. You can see the number of triangles difference between the LOD 0 here and LOD 3. So mipmaps and triangles are all fantastic. I can talk myself blue in the face about them and how important they are to use them. And please use them, please do, except for when you shouldn't. So there's very few elements, very few times that this will come up in certain games, but they are there, and I just wanted to touch on them. If your camera's not going to be moving around, the geometry is going to be static and not moving closer or further away, you won't be needing mipmap, you won't be needing LODs here, mostly because they're never going to be changed out, so it doesn't need to happen. And you're also not going to need these when your camera is going to be static, because if you're not moving, why do you need to change things out? So another thing to do would be to avoid duplicate vertices. This can happen for a number of ways. It can happen when you're modeling your geometry and you're just copying things around, adding vertices as you will be. This can happen between different shaders or kind of how you're processing your verts. Just be a little careful and keep this in mind, because adding vertices on top of each other is just going to cause the GPU to have to render that one space on the fragment multiple times, and there's just no real reason to kind of do that. So next, let's go ahead and take a look at shaders. So use medium P and high P keywords. This is really kind of important. You don't really need to use low P, because in current generation GPUs, they treat low P just the same as they do medium, so you might as well just use it anyways. Don't use full 32-point precision for anything that kind of doesn't need it. Generally, you're only going to need this for vertex positions. Avoid loading a 32-bit data into a buffer and then reading out as a medium P attribute. This is just some wasted power. It doesn't need to happen. Just pay attention to your shaders and kind of what's going on here to keep that performed. Avoid complex mathematical operations. Transcendental math functions are super expensive, so avoid using things like power, exponential, log, sin, and tan. If you're using a retail engine like Unity, avoid writing your own operations like normalize, dot, inverse, square root. There's built-in functions into these engines that will ensure the driver is going to generate some better code. So while it is super fun and interesting to kind of write these yourself, go ahead and use the ones that are in the engine. It's going to save you a lot of performance in the end. So the next thing you want to do is you're going to want to avoid heavy overdraw. Unity and Unreal both give you really easy ways to kind of see the overdraw that's happening in your scene. Here you can kind of see us using this in Unity. What overdraw is when you have to draw a pixel multiple times, because there's levels of alpha blending on top of it over and over and over again. So the hotter it is, you kind of see on the screen, the more overdraw it's happening, therefore the pixel's more and more expensive. So one of my favorite things to do when I'm profiling an application is to get to a heavier part of the game and then start opening all the menus I can. The reason I do this is because when you start, the reason I do this is because when you add all these additional layers of alpha transparency, which is generally what you see in a lot of UI, it starts adding even more and more weight to the scene and can make it really heavy. It's a good way to kind of see if you're taking all the overdraw to account. So one good way you can kind of manage overdraw is make good use of arrangement of layers, sorting the layers, rendering queues, camera settings. Do anything you can to try to avoid this because it's going to save you a lot of power. So another way you can do, another helpful thing is you can reduce the amount of alpha blending and tested fragments that's happening. So if you look at the little sprite down here at the left, you can see the sprite. We take out the opaque parts of the sprite that we kind of know, and we also separate it out from the transparent part. We put the opaque part in front and then the transparent part behind. The reason we're doing this, is because it's going to cut down on the amount of alpha tested pixels that the GPU is going to have to do. When it knows that there's this opaque part, it knows it's not going to have to draw anything that's behind it, which it kind of has to do with transparency. This is kind of the same reason with sprites. If we move over to the items on the right, you want to try to use polygons to reduce the amount of empty space on your alpha textures. This is all that empty space is just going to add to the overdraw pixels and isn't going to really kind of help your scene any. So adding a little bit of geometry here is going to help you get some performance. Another thing you're going to want to do is experiment with dynamic branching. It's not as expensive as most developers think they are. There's been a lot of updates kind of how this works. So both sides of the branch will be executed and one will be picked if the branching area is too small. Shader compilers are going to automatically optimize this nowadays. So go ahead and experiment with it, see how helpful it'll be to your project. So let's go ahead and take a look at frame rendering. So render state switches are very, very expensive. Please avoid trying to use them whenever you can. Render as many primitives as possible in one draw call. When you open up your profiler, don't just check the number of draw calls or batches. This isn't going to give you kind of the real kind of look at everything, because not all draw calls are the same cost as other draw calls. Using tries and set passes is going to be a little bit more accurate. Batch as many things as possible. Use static batching, GPU instancing, dynamic batching. Udemy makes GPU instancing really easy nowadays. With URP, try to do anything you can just to try to reduce the performance or help your performance here. You're also going to want to reduce frame buffer switches. Make sure you bind each frame buffer object only once, making all the required draw calls before switching to the next. Avoid unnecessary context switches. And of course, use frame debuggers to kind of check. Here we're using the Unity one. Unreal has theirs as well. Pay close attention to this. It's going to save you some performance. So after rendering, the GPU will write the result of the external memory from tile memory. You'll want to minimize the writing to external memory wherever possible. Disable writing to depth/stencil buffers if not used. Be sure to use the Unity frame debugger to kind of check, kind of highlights if this is kind of happening on the frame, and you can just easily go in there and fix it. So a few other little VR graphics tips. So color space is a model which represents the numerical values which each color is assigned. It also describes the amount of area that each color will be allocated. Linear color space allows for the values of multiple light sources to easily and accurately be accumulated within shaders, whereas gamma space in this edition would not be physically accurate due to the curve inherent to rendering the gamma space. Rendering in linear color space also brings benefits to aliasing by helping to reduce specular aliasing. Specular aliasing can occur in gamma color space because objects become increasingly bright. Linear avoids this problem by increasing the brightness linearly. So if you're wanting to reduce any special crunchiness there, linear, go with linear. It's going to be fantastic to kind of help you with that problem. So level design can really influence kind of the way you start seeing aliasing in your scene, especially in VR. So some things you're going to want to avoid: avoid long edges and thin bubbles, micro triangles, of course, but also aliasing now. This will help reduce those aliasing. When modeling edges of meshes, avoid some sharp or sudden edges. Wonderful to kind of help there. Anything that you kind of need here, use LODs to kind of hide these and just kind of add in the detail where you need when the users are close. So alpha compositing is the technique of combining an image with a background image to produce a composite image that has the appearance of transparency. Alpha testing is the most widely implemented version of this, but it can produce some severe aliasing effects with the edges of objects. This happens because the alpha channel is bitwise, so there's no blending on the edges. Alpha to coverage is another method of compositing. It can help reduce aliasing by transforming the alpha component output of the fragment shader into a coverage mask, and combining this with the multi-sampling mask before using an AND operator, then only rendering the pixels that pass the operation. So that sounds really overwhelming if you're still kind of new to shaders and kind of how this all works. Don't worry, we have a step-by-step guide way of implementing these on our developer page that I will have a link to here in a minute. So shadows are really expensive. Shadow mapping is also just super expensive on mobile. Low resolution shadow buffers result in large amount of aliasing as well, so you're not going to get the highest resolution shadows. Anywhere you can, use blob shadows and cookies where possible. It's a fantastic optimization, especially for a VR set like the Quest. It's going to give you some wonderful savings. So we have some additional resources for you. Please check out our VR best practices. That's going to have the compositing implementations for you. We have an ARM guide for Unity developers. We have one for Unreal developers. We also have our technical artist guide that kind of covers a little bit more of the art elements, a little bit more in depth. But thank you, everyone. If you have any more questions, please hit me up on Twitter. And thanks for hanging out.